In this problem, we have a guitar string that we are plucking, and we want to see what is going to be its behavior after we release it from its initial position. So we are trying to find what we are going to be calling W of xt, that vertical deflection of the string for all points in space from 0 to L, and for all points in time after we release it from its initial position. And we also are going to want to find what note it's going to produce, which we'll be able to do once we know the natural frequency of this string. So really what this is going to be is we want to find the natural frequencies, which we're going to need to do as part of this, and then convert that into the tone or the note that we would perceive. So we want to start here with the model and the equation of motion are going to be kind of the same step. In this case, we're not going to go through in a lengthy modeling process here, so I'll kind of combine these into one. First, what we're going to need to do is be able to define this as a string type of problem and a limited string type of problem that we are going to be able to find W of xt from. So in this case, we are told that we have this linear density of rho of 57 grams per meter. So that is going to mean that rho is constant. This is a homogeneous string, and it's not going to be changing in time. So rho is constant, and the tension, which we usually call P in these problems, is 50 kilonewtons, and we're told, or it's implied, that that is also going to be constant. So these things are constant. We are also told, and this is important for the equation of motion, that F is 0. We are giving it this initial condition and we're letting go of it, and it's just based on the initial conditions how its behavior is going to be determined. There's no external forcing once we let go of this string. So because those are the cases, that's kind of wrapped into the modeling. The modeling step we already did in the previous videos of making that differential slice, coming up with our f equals ma, so we're not going to redo that again. As long as we can see that this is that string type of problem, we can kind of jump right to the equation of motion step, and we have this c squared del squared w del x squared equals del squared w del t squared. So this is going to be the equation of motion for this system because we identified it as a string, and it had constant density, it had constant tension, and it was free vibrations. So that is the equation of motion, and we can identify, we kind of put the identify step in here as well, because we want to know what is the solution going to look like here. So again, this is a string type of problem, and we have, I'll just rewrite it here, P and rho are constant, and rewriting that it's free. Free or autonomous. So that means based on the equation of motion we have, it is separable. So W of xt, we're going to be able to write as a W function of only x times a capital T function of only time. And that's going to be important in our solution process. And then the general solution is going to look like an infinite series. So it's going to be this infinite series, n equals 1 to infinity of, we'll have the eigenfunctions times, now the eigenfunctions will be its own step here, but those eigenfunctions times a cn cosine omega n times t plus a dn sine omega n times t. So we're going to need to determine the natural frequencies, all infinite of them, the eigenfunctions, which are going to relate to those natural frequencies, and the cn and the dn coefficients, which will have an infinite number of those as well. So that's what we need to fill in order to get that closed form solution, which we will be able to do because of kind of the simplicity of how the system is put together, and because we're about to see we have homogeneous boundary conditions. So in what I will classify under this parameters step, we need to get omega n, wn, cn, and dn. So we're going to start by looking at our boundary conditions. So this will be kind of a substep of this. Let's use our boundary conditions because our w of x solution is going to have the general form of this a cosine omega over c times x plus b sine omega over c times x. So as part of this, we have this c, which we can calculate later. It's just a standard calculation. We don't need it for this step right now. But we need to apply the two boundary conditions that we have. So for this, we need to see where do we know w, the vertical deflection, or where do we know w prime, the angle. And in this case, with this string, looking up here, it is, we can say, pinned at O, and it's pinned at L. So what we can say definitively, and this is true for probably most string problems, is at 0 and at L, x equals 0, x equals L, we know what the deflection is at all points in time. It has to be 0. Those points cannot have a non-zero value for w. So that comes down here into our boundary conditions. We can say that w of 0 is 0 and w of little l is 0. Those are the two boundary conditions. And they're going to give us two algebraic expressions. So let's apply that first boundary condition. W of 0 is 0. And we can put it into the equation for w of x, because that's going to tell us that a times the cosine of 0 plus b times the sine of 0 is equal to 0. So just plugging in 0 for x there, well, sine of 0 is 0, and the cosine of 0 is just going to be 1. So this tells us that a must be 0. So that's going to then satisfy that first boundary condition as long as that a coefficient is equal to 0. So what I can do is I'll come up here and I can get rid of it really from this w of x. Since a is always 0, then my w of x must be this b sine times omega over c times x. And my second boundary condition then, w of l is 0, and that will ensure that that other pin at L, where the string is attached, that its deflection is always going to be 0. So I don't even need to include that a expression because I already know that a is 0, so this is going to be b sine omega over c times L when I put in x equals L. So this is where we need to think of having a non-trivial solution to this problem. We could say, and it would mathematically be true, that if we just make b equal to 0, that would satisfy this second boundary condition. However, that would then mean that w of x would equal 0. And that would mean that there's no deflection in the string because always the deflection everywhere would be 0. But we know that's not true because we're giving the string that initial pluck and making this triangle-shaped deformation in the string. So this cannot be the case, right? Because that would give us a trivial solution. So instead, that means we still have to be able to satisfy this boundary condition, but we can't satisfy it with b equals 0. So instead, this omega that we kind of invented as part of this process, that must be the thing that's going to make this equal to 0 and satisfy this boundary condition. So the b, because it cannot be 0, I can actually just divide through by the b and not worry about it right now. So this must be true. It's not the b that makes the term 0, it's the sine omega over c times L that makes this expression 0 and satisfies the boundary condition. So what can we do? We need to choose an omega that makes this true. C is already determined for us. That's based on material properties and the tension. L is the length of the string, so it's this omega. So what I can do is I can take the inverse sine of both sides so that the right-hand side I am left with omega over c times L. And I can take the inverse sine of 0. So really what I want to think of here is what values, when I take the sine of it, are going to give me 0. And there's not a unique solution to that, and this is what gives rise to our infinite natural frequencies and our infinite mode shapes, or eigenfunctions, as we're about to see. So for example, like I actually saw in the first part, if I take the sine of 0, that's 0, but actually that's going to repeat every pi radians. The sine of 0 is 0, the sine of pi is 0, the sine of 2 pi is 0, and so on. So what I can say here is that there's an infinite number of solutions, but they reoccur every pi radians, where n, always for these, is going to be an integer. And actually we do start at n equals 1. We're going to ignore 0 in this case. So n is going to take the values of 1 and 2 and 3, etc. So n equals 1, 2, 3, an infinite number of them. So it's this periodicity that when we rearrange this now, I want to solve this for omega of sub n, because there's going to be an infinite number of them. So that is both an indexing term because we can have w1, 2, 3, 4, 5, but also it's n because these are the natural frequencies of it. I can multiply by the c and divide by the L. So nc times pi over L is equal to omega n. So my first natural frequency is when I evaluate this at n equals 1, then my second natural frequency at n equals 2, and so on. And n will go up to an infinite, into infinity, and that's what gives me all of the natural frequencies of this string. This is a continuous system. It has an infinite number of natural frequencies. Right, so I'm going to put this in a box. This is crucial to know that these are the natural frequencies of this string. And the natural frequencies now we're going to use in our w of x to make our eigenfunctions, which is w sub n of x. So let's see here. I already said a was 0, so I'm left with this b term, and we'll see that the b also will go away. I'll leave a b for now, but I'm going to get rid of it soon. Sine of omega, we now know the values for, is this nc pi over L. So this will be n pi over L times x. I have a c in the numerator of omega n, but a c in the denominator inside the sine function, so that's why the c is going to go away. And here, these are my eigenfunctions. And I could also rewrite this as b sine of omega n over c times x. And either would be fine because the natural frequency has that c in it. Now, for the moment I have that b there, I'm actually going to get rid of it in a second because that amplitude is not going to matter, because we can go back now to our general solution for little w. And remember, that was this summation from n equals 1 to infinity of our w sub n, which for the moment I'm going to write out this way so we can see where does that b go and why can we ignore it. Times cn times the cosine of omega n now times t, that's the natural frequency, plus d sub n sine omega n times t. So what's going to happen is I have this b on the outside. I can distribute that into the cn and the dn. And that's why, because I haven't figured out cn or dn yet, I can just have them absorb this b when I do my solution. So instead of including a b in the eigenfunction, I'm going to get rid of it, and it will be accounted for when I solve for cn and dn. So that's why the b, or whatever coefficient is left over in my eigenfunction, I can just get rid of, and it's going to be simpler in that next step when I solve for cn and dn to just look at my eigenfunction as this sine in this case. So I have the eigenfunction is done. I will also put a box around that to remind us that we have the eigenfunction found, and I'll leave it in this form since that's how I'll be doing the integration step next. So natural frequency omega n, eigenfunctions or mode shapes, Wn, we have, and those again are based on the boundary conditions. Now we can move on, and we are interested in finding the Cn and the Dn, and for those we are going to need our initial conditions. So our initial conditions we want to define, and we're going to get those from up here. We are plucking the string in that we are going to hold it in this triangle shape, and then at time of 0 we let go of it. So we need to define across our entire 0 to L space what is the initial position of that string. In the middle it's equal to h, and on the left side and the right side it's equal to 0, and it's going to be a linear slope in between. So for our initial conditions, let's define here w of x0. So what's the position as we go from 0 to L in x? Now it's going to be a piecewise function. It's going to be that slope up for the first half and then the slope down for the second half. So for this one, we can define it as 2h over L times x for that first half, x between 0 and L over 2. Right, so check this. If I put in 0, I get 0 for w, so that's good. If I put L over 2 in, then I am going to get just h, which is what it should be, because at the middle, that height is equal to h. And we see that it has a positive slope, so it's going to be linear in between 0 and L over 2. And then on the second interval from half to L, or half of L to the full L, I see that I should have a negative slope, but still has to satisfy h in the middle and 0 at L. So for this one, one way I can define it is 2h L minus x over L. There's other ways I could have written this, but this works, just testing it at the boundaries of the interval. Putting this in here. At L over 2, this is going to be equal to h. And when x is equal to L, I get 0 on top, so w is going to be equal to 0. So as far as the position goes, these now define the position initial conditions. And again, I can do it as this piecewise function. And for the initial condition on velocity, we can say that it is going to be 0 everywhere along the string, because we are holding it at rest initially in that triangle position, and then we are simply letting it go. So the initial velocity across the entire string must be 0. So using these initial conditions, really the W1, let's go back up to our parameters, because now we are ready to find the Cn and the Dn terms. So the Cn, it was defined as I went 2 over L, the integral from 0 to L of my eigenfunction times my initial position, dx. So if I write this out a little bit, 2 over L from 0 to L, the eigenfunction was that sine of n pi over L times x, and my initial position is that piecewise. I won't rewrite it right here, but that's the integral I want to carry out. We could do this by hand. I have a sine function times a linear function, and that would be one way to do it. I'm going to instead do this using Mathematica. To find this Wn is going to be sine of n pi x over L. And run that. Okay, so our eigenfunction is defined that way. And now we need to define that W0. And this is that piecewise function. Get down to it here. And we have it defined here, so I can use piecewise. So escape PW escape lets us do a piecewise function. And if I press the control comma, I can put in the definitions here. So for W0, the first piece of it, using this, is going to be 2h over little l times x, and that is good for 0 to x less than L over 2. looking again at that definition. And then the second piece of this, we can use that second line here. So that is the 2h L minus x over L. And that was good for L over 2 less than x less than L. All right, so now the W naught is defined and Wn is defined as well. So I'll just suppress these for the moment. And now I can go up and actually do that integration and let MATLAB do it. So let's put out in front 2 over L. And I want the integral from 0 to L of my Wn multiplied by my W of 0. And we can let it do the hard work for us of the integration. Now we see it didn't like that because there's a lot of variables in here and it doesn't know what to do with some of them. So what we can do is give it a little bit more information and then it's going to be able to hopefully do this. So one, it doesn't know that, that things are real. It doesn't know what the value of L is. So we can just, we want to do this generically, we can tell it that L is a positive number. Okay, and it was able to do some of the work for us. So now it liked that because it knows it's integrating from 0 to a positive number rather than 0 to a negative number. It gave it a little bit more information. And we can also say that n is going to be a member of an element of the integers. And if we tell it that, we get even more simplifications happening. So it comes with this 8h times the sine of n pi over 2 over n squared h squared. So let's record that. And I'll just write that here by hand. So we have 8h over n squared h squared, pi squared, times the sine of n pi over 2. Now, actually, this we can have a little bit simpler because sine of n pi over 2, because n only takes integer values starting at 1, we can have sine of pi over 2, well, that's going to be equal to 1. But when n equals 2, it's going to be the sine of pi, which is going to be 0, negative 1 is next, 0, 1, etc. So what's going to happen is that Cn for all the n values is actually going to be 0. And it's going to be either 8h over n squared pi squared, either positive or negative when n is an odd value. So we could leave it like that and MATLAB is going to be able to handle it. But another way we could write this is 8h over n squared pi squared times negative 1 raised to the n plus 1 over 2 power. And that's going to be true for odd multiples or odd values of n. And it's 0 for all the even values. And we'll see why this does actually can condense our solution a little bit. So if we see this exponent I put on here, this n plus 1 over 2, we can see what happens here when n is 1. We get 2 over 2 is 1, and it's negative, as it should be. But when n is 3, I get 3 plus 1 is 4 over 2, so that's going to be negative 1 squared, and that's going to be positive. So this is a way we can have alternating series on the odd values of n, and then we've just defined it as 0 for the even values of n. And the dn, because we saw that our initial velocities were all 0, our dn is also just going to be all zeros in this case. Because when we do, we know it's defined as 2 over L times the integral from 0 to L of this omega n w of n x w dot of x0 dx. But again, everywhere this is just 0, so that makes the entire thing equal to 0. And that's true for all values of n. All right, so let's come down here and assemble our solution. Let's look at in the identify what it should look like. All right, so it's going to be that summation of our eigenfunction times the Cn and these Dn terms is how we're going to put it together. So let's see here. We have our W of xt equals the summation of n equals 1 to infinity of our eigenfunction. I'll copy that in. Remember, we got rid of that b. It got absorbed into the c and the d term. So sine n pi over lx. And that gets multiplied by our Cn cosine omega n t plus dn, which is 0 in this case. So let's see what our Cn value was. We have it over here. We could do it as the piecewise, or I'll write it in the long form for the moment, that with that sine n pi over 2. So we had 8h over the n squared pi squared sine of n pi over 2. So that is c sub n, and that gets multiplied by the cosine of the natural frequency times time. And again, in this case, our natural frequency was n pi c over L times t. And we can close that bracket. In this case, again, the d value was 0, so that simplifies this a little bit. I can simplify this a little bit further if I want to, because of the nature of this sine of n pi over 2 happening. I know that every even value is actually going to be 0, because the dn are all 0 and the cn are 0 on even values of n. So I could say that this is the summation on only odd values of n, would be a way to write this. And then I have 8h over n squared pi squared times the sine of n pi over L times x, that's the natural frequency over c, and times the cosine of n pi c over L times time. And that would be an alternate way to write it that's a little bit more compact. It gets rid of that sine of n pi over 2 term, and then this is going to be our exact solution to this problem. Closed form, we just need to take an infinite number of terms to get that exact solution. So it doesn't look like much. We can't really picture what this is doing too easily. We're going to plot it in MATLAB in a second, but some things we can look at here. If we look at, as we add these values, as the value of n increases, we have that n squared in the denominator of this function. So what's going to be happening is that that amplitude, that 8h over n pi squared, is going to get smaller and smaller and smaller as n gets larger and larger. So the addition, the strength of higher frequency terms is going to get less and less as that frequency increases. So as n gets bigger, the contributions to W are going to only get smaller and smaller. And we'll see how this is reflected when we plot this, when we simulate its results. Going into MATLAB now, there's still actually a parameter I did not yet calculate that I can. I'll put in those given values of the tension P was that 50 kilonewtons or 50,000 newtons. The value of rho I'm putting into standard units or base units of kilograms per meter. Remember, this was the linear density that we were given, 57 grams per meter, so 57 times 10 to the negative third kilograms per meter. And then we can calculate that C. Remember, C for a string is the square root of P over rho, where rho is the linear density. So let's just see what that C value is. So we got 936.5. And we'll be using that in a second here. Then the other given information, the length of the string and the height at the center, I can put those in as well. I'm going to simulate this for 0.1 seconds, and you'll see that's going to be more than enough because the oscillations in these types of systems are typically very fast. So t only will go to 0.1 seconds, and I will divide my space into 1,000 pieces. Now what I want to do is I'm going to make my W function here and I'm going to make it actually a matrix because I'm going to want every column of it to be a space. So that's going to be my x values are the columns of W, and the rows of W are going to be the timestamps because W is a function of both space and time. So I do want to pre-allocate it here. So I'm initializing it, and I do need to run everything up to that point. Okay, now I can define my natural frequency, which we found analytically. That was the n pi c over L, and I'm going to make that a function of n. So I have my Wn, so I can find the first natural frequency, for example, and I'll come back to this in a bit. That would be our first natural frequency in radians is about 4,900 radians per second, and then we can find the second natural frequency, and so on from there. Okay. Now I'm putting in here that summation, and that's I'm going to do this one for 48 terms, or not 48 terms, but n equals 48 is the maximum. So we have to truncate it somewhere. I'll do it pretty high at 48. And remember, all of the odd terms have values, and the even ones were all 0. So in this for loop here, I am only doing odd values since I know it's going to be 0 otherwise. Now, it's not a big deal. I could have defined it using that sine of n pi over 2, but I am using that kind of a little bit more compact solution in the way that I'm doing it. So I'm going to add all of my terms together as I go and fill in W row by row. So if you see how I'm defining W, I am going to do it in this nested loop here. I'm going to do it for every timestamp, and then in the inner loop is where I'm doing that summation over n. So let's say for the first timestamp, I'm going to go through here for 48, for n up to 48, and find that row of W. Then I go to my outer loop and I go to the second row of W. That's going to be the second timestamp, and I do the same thing. I'm going to do my summation, and I'm going to come up then with that second row of W, and that's what I'm doing in 24 is kind of tallying up that value for W. So by the end of this loop at 26, all of W is filled out. So let's just run that part. And again, looking at the values is not going to tell us very much information, but we see that W is this, or little w is this large matrix of values. All right, so that contains all the information we're interested in. Now I will animate the result. Because this is a dynamic system, I really, to be able to visualize this, would like to animate it because I want to know what's happening across the length of the string from 0 to L, and then I can update it for every timestamp. And that's exactly what I'm doing with this animation here, is I'll be updating it timestamp by timestamp, and I have to slow it down to be able to even observe it, because in reality this is oscillating really fast. So I'm not going to be able to look at it in real time, but in this slower simulated time. So let's look at this animation here. So really slowed down, this is what the string is going to be doing. It goes up to that initial peak of h, and then it comes down, it's kind of flat, and then it goes in the opposite direction down to negative h. Now, keep in mind here, we did not account for any dissipation, and we don't account for dissipation when we are putting together this equation. So it is just going to oscillate up and down, and it's going to keep doing that forever because no energy dissipation is going to be included in the model for this system. So it's just going to keep bouncing up and down. So I'll stop that because it just keeps going over and over and over again. And so that's the animation. That's what W of x and t is doing. So let's go back to what we were trying to find here. We wanted W of xt. Well, we have that. That part is done. We want to know what musical note the string produces. And we can look at this a couple of different ways. One way we can do this is actually looking at a power spectral density. Now we have an infinite number of points between 0 and L on this string. What I'm going to look at is just one of those points. I want to know what's happening to just one point, and I'll pick here the middle point. So I'm only picking out W, the 500th column of W, which is basically that middle point. And I want to see what it is doing versus time. So let's just look at tracking that one point. And now, because it's only a single point, I can plot it over time. That's not too interesting to look at, but I can see over that 0.1 seconds, what is it doing? So at the midspan, I'm just going to look in time, what's happening. And let's just zoom in to something more interesting. All right, so it has what looks to be basically this triangular wave happening as we go forward in time. But I want to look not at its in the time domain, I want to look in the frequency domain. So I am going to do a power spectral density of this point, of this plot that I just made. So what frequencies is this oscillating at? Where are these powerful frequencies happening? And I'm actually going to do this with pwelch. So it's going to give us a little bit better quality than we've been working with. And you can look up how pwelch works in more detail in the documentation, but it's going to be doing that power spectral density kind of all built into one. It does the Fourier transform for us and then calculates the power. And I'm going to calculate the frequency in hertz. It's going to come out by default to see what's happening to that midpoint. All right, so let's see what's happening here. So we get a nice quality power spectral density plot, and we can see where these clear peaks are happening in the frequency domain. So we're seeing a peak here at 781. And keep in mind, this is in hertz. I could convert it into radians if I wanted, but I'll work in hertz for now. And then I see all of these very strong peaks happening subsequently. So here at about 3 times larger, we have 2344, and 5 times larger, 3906. So remember, we're not seeing peaks at the even multiples because it kept going to 0 the way that this string was constructed. Because of those boundary conditions, all of those C terms went to 0. So on these odd multiples of the frequency, we are seeing peaks, but they are smaller peaks happening. So what's happening here? Well, this is a string that's vibrating, and in fact, I used parameters here that were going to be representative of a guitar string. So the tension that it's under as we are wrapping it and tensioning it from the fretboard to the bottom, 50 kilonewtons is not that unreasonable. And the density of the string, the linear density, is going to be dependent on the material that the string is made out of, whether it's going to be a metal string or a nylon string, and also its cross-sectional area. Those two factors are going to determine that linear density, the rho value of the string. So how much it is in tension, P, and that rho value are going to determine the value of C. And C is going to determine what the natural frequencies are. And that's what we're looking for in a string, is we want specific natural frequencies. And really what we're doing by choosing the C, by what material and what cross-section the string is made of, and by how much we tension it, we're choosing the C, which chooses the natural frequencies, which chooses the pitch of that string. So in this particular case, that omega 1, that first natural frequency, is occurring at 781 hertz. And we also see that that is the largest peak. That is the fundamental frequency, has the most power. And then as we go forward, those higher frequencies have less and less power. But in this case with the string, we are seeing that all these peaks are happening at those odd multiples. We're getting some of those overtones, we call them, in the string. Now, this is a simplified model in that the string is operating in complete isolation, but when we pluck it and we let go of it, it is going to be vibrating at an infinite number of frequencies, not just the fundamental one, but these higher frequencies as well. However, the one with the most power, the one that we're really perceiving, is that 781 about hertz oscillation. And that's how we would identify the tone of this string. And if we were to look up, 781 hertz is fairly close to 784 hertz, which would be a perfect G, specifically G5. So we would need to change the tension on this. We would need to increase that natural frequency to 784 hertz if we wanted this G string to be in tune. Again, that's what we're doing when we're tuning the guitar, is there's going to be an expectation of what frequency the string should be vibrating at. Should it be, like in this case, G or E or some other note, and then we can be flat or we can be sharp if the actual frequency at which we're vibrating is lower or higher than that target. And that's what we're doing when we are increasing or decreasing the tension in the fret, is we're effectively changing the value of P, which changes the value of C, which changes the natural frequency of that string until it is in the desired value. And because this is a continuous system, it is not only oscillating at a single degree of freedom, which is how we idealized it earlier. It's going to be oscillating at all of these tones. And that's where these overtones are coming from. But the fact that the power is highest at that fundamental frequency is why we're going to perceive it as a G5 or very close to a G5, but it is not a pure tone like we would generate on a computer or something that was truly a 1 degree of freedom system. So to answer that last part, what is the note that we would say this string is producing? Well, we already determined it through MATLAB, but coming down here, let's look at that natural frequency, NC pi over L. The fundamental frequency is the one that we're going to perceive here. So what we're looking for here is that first natural frequency when n is 1. So that will happen C pi over L. So let's come down here. Omega 1, that fundamental frequency is going to be C pi over L. And what we're going to get is, based on the given information, that this came out to, when we calculated, about 781 hertz, which is close to, but like I said before, the 784 hertz, which was the G5. So if we tune it up a bit, G5 would be the note that it produces.